Lecture, I will talk about the EEG and MEG forward problem. To start with defining and introducing the concept of forward problem, I have to do a little step back and talk about source reconstruction. The main idea in source reconstruction is that we have a signal. For example, in this case, could be a shadow, and it's not always obvious what the source is. So the same applies for the EEG and MEG source reconstruction, where we have some data. In this case, for example, MEG data, and from this MEG data, we want to reconstruct the sources which have generated the data. And this is a so-called inverse problem. In order to solve this inverse problem, we have to go the way back. So we put some data, some sources in the brain, and we compute the electric potential, the magnetic field that is generated by this data. And this is called the forward problem. The EEG forward problem. So solving the EEG forward problem means solving a partial differential equation. I don't want to scare you. This is the model underlying the EEG forward problem, where we can see that the goal is to evaluate the electric potential U. So here we can see various variables. What we are interested in is the U. U is the electric potential. Then we have some other protagonists here. We have JP, that is the current density, and we have omega. In addition, we have the conductivity, sigma, which varies depending on which compartment of the head we are considering. And JP, a dipolar source. And omega is another crucial element of this model, where this is the geometry where we want, or the domain where we want to solve our problem. And if we have a sphere, if omega is a sphere, then U can be written analytically. There is an analytical solution. If omega is a more sophisticated or more realistically shaped head model, then we have to go for or look for a numerical solution. In the MEG case, the goal is to evaluate the magnetic B field, B. We have B of R, which is relating the magnetic field B, which will be evaluated outside of our head, our domain, and is an integral. And what we have to focus is, again, we have omega, and we have J. J can be split into two contributions, JP that we saw already before. JP is the dipolar source, and JS is the current that is flowing in the volume conductor, is the secondary contribution of the secondary electric current density. And this JS, in particular, is the one that depends on the EEG forward solution. So here we can see directly the link between the EEG forward problem and the MEG forward problem. So at first, we have to solve the EEG forward problem, gain our U, and then embed the U in the JS and compute the B field. Again, when omega is a sphere, we have an analytical solution for the MEG forward problem. When omega is not a sphere, we have to go for a numerical method and find a numerical solution. Okay, this was showing equations. If we want to have like a simplified version of what I said, we can summarize saying that in the EEG case, we have to compute the potential in the head omega, knowing the source JP. And the values of the potential at the electrodes is the solution. And this is a representation where we have a dipole, and then the current, and then the electrodes, which can detect the current, as Sophie already explained. In the MEG case, we have to compute the magnetic field B, this time outside of the This is working? It's not working? Is this working? Yeah? Yeah, okay. Okay, sorry. In the MEG case, we have to compute a magnetic field outside of the head, knowing the current JS inside of the head. And the values of the B field at the coils is our solution. So again, here we have the representation of a same dipole Then the red lines are representing the B field, and we have coils to detect the signal. We can also say that when we cannot assume that a sphere is a good representation of the head, we need to use numerical methods. Otherwise, we have an analytical solution. Which are the ingredients of our problem? First of all, we need a head model where electrical and geometrical features are merged together. This can be a sphere or a multi-layer sphere, or more realistically shaped head models. The second ingredient is the sensor model. Then we need a source model and a method to compute our solution. There's a vast spectrum of different numerical methods, and I will explain, or I will say something about some methods. But first of all, I would like to focus on the head model. So some general consideration on the head model. First of all, the human head is a volume conductor. This in particular means that currents are generated by the brain, and currents can flow through the head tissues. So a crucial parameter, as we saw already from the model, is the conductivity of the head. Furthermore, we did a digital representation of the human head, which can be transported in our PC, for example. And the degree of realism varies a lot. So we can start having a spherical representation, or we can have a more sophisticated representation with, for example, anisotropic conductivity. And there are imaging techniques like MRI, T1 or T2 weighted, and CT, which can help creating a realistically shaped head model. So as to regard of the head model, we have geometrical and electrical features. For the geometrical features, the geometrical representation of the human head can have an increasing accuracy, as I said before. So we can have, for example, a sphere. In this case, we had 4-compartment sphere model. So the inner part, the blue part, will represent the brain compartment. Then we can have the green part representing the cerebrospinal fluid, CSF. Then the yellow will be the skull compartment, and then the red one will be the scalp, so the skin. The same version can be more realistic. So, for example, we can have a 3-compartment model from an MRI image. Here we have the 3 compartments, so brain, skull, and scalp. We can increase the accuracy, and we can go for a 4-compartment model. Here we added the CSF compartment. And again, we can do a step further. Within the brain, we can distinguish between white matter and gray matter. And also here in the skull, you can see some orange part where we separated the spongy part of the bone and the compact part of the bone. As to the electrical features, the accuracy cannot be improved so much, in the sense that, and for many reasons. So there's a huge variability between tissue conductivities. If we think of the brain as a wire, we can associate the conductivity of the CSF to the copper part of the wire, so very conductive. And the skull can be associated with the gummy part of the wire. So the skull is working as an isolator in our head. Furthermore, there is also a huge variability between humans. So it's not easy, or it's not even possible to assess the individualized conductivity value for each subject or patient. So in practice, the conductivity values are inaccurate and they are not individualized. And in general, standard isotropic constant values are considered. But we can do something for the white matter, in the sense that we can extract information from DTI images and deduce the white matter anisotropy. So here we can have an individual value for the white matter compartment conductivity. And there are some techniques which can be used to individually calibrate the skull conductivity. As to the sensor model, the main thing is that the coordinate system of our EEG and MEG sensors should match the coordinate system of the head model. So fiducial can guide the co-registration. For example, in our case, patients or subjects who are going into the MRI machine will have fiducials representing landmarks like the nasion and the two preauricular points. And this fiducial can be used also in the EEG and MEG recording, so also this other fiducial will be recorded as further electrode position somehow. So we can match the fiducial that we got from the MRI and the EEG or MEG recording session. In this tutorial, we will, as we have CTF MEG data, we will co-register the MRI, EEG, and the EEG sensors in the CTF coordinate system. This link is in this link you can find an overview of all the coordinate systems that are mainly used in our field. This is a representation of the CTF coordinate system. Yeah. As to the source model, we talked about before the dipolar source, JP, and we have to provide a list of positions and orientation of our dipoles. And the source model accuracy depends on the head model accuracy. For example, if our brain compartment is more or less already accurately represented by this mesh, then we can create a grid and distribute uniformly positions inside of the brain compartment and consider those positions as dipole positions. And for example, the orientation will be the Cartesian one, so X, Y, Z. If we have a more accurate head model, so we can, for example, via FreeSurf or other tools, we can extract the white and gray matter surface. We know that the sources are in our brain represented by these pyramidal cells, and we know that pyramidal cells, neurons, are oriented perpendicularly to the gray matter, so we can fix the orientation constraint when we have a more accurate representation of the gray matter, for example. As to the method that we can employ to solve, in general, partial differential equations, in our case, the EEG and MEG forward problem, this is a list. We can start with or we can choose between boundary element method, BEM, finite element method, finite volume method, finite difference method. Within the big family of the FEM, there are sub-families. For example, we can have a standard. The standard FEM can also be called as continuous Galerkin FEM. There is also a discontinuous Galerkin, unfitted discontinuous Galerkin, Kant-FEM, mixed formulation, immerse, and all of these methods have been so far employed for solving EEG and MEG forward problem, or EEG for sure. Yeah, and today, or now we will, these are just some references, and today we will be dealing with BEM, so we'll say something about BEM, we'll say something about the standard CG FEM, something about the DG FEM, and that's it. Yeah, so for the boundary element method, the crucial point is that we have a triangulated surfaces. So the triangulated surfaces are describing the boundaries of our head compartment. So we're dealing with surfaces. And usually the compartment that are considered, so each compartment is homogeneous and isotropic. And usually the head compartments that are considered is the skin, the skull, and the brain. But also other and more complex geometry can be included, like ventricles or holes in the skull. As to the FEM, we have a tessellation of the 3D volume in tetrahedral and hexahedral. So with BEM, we were dealing with surface meshes. In this case, we need a volumetric mesh. And each element of this tessellation or mesh can have its own conductivity. So in this case, for example, it's easy to embed the anisotropy of the anisotropic conductivity, which is not possible in BEM. The head compartments that we will use and or that can be used or usually used are the skin, the skull, the CSF, gray and white matter. And additionally, the anisotropy of the white matter can be an important feature to be added. So FEM in general is an accurate numerical method, but is computationally quite expensive. Yeah. Now I would like to try to introduce the idea that is behind the DG FEM. And to start with that, we can visualize an automatic segmentation of the inner and outer skull compartment. And if we zoom in, we can see that the output of, so in the yellow line, there will be the output of the automatic inner skull compartment. In the purple, we see the outer skull compartment representation. And we can see that the purple line has is generating some errors. So in these points here, the segmentation is failing because compartments that are belonging here to the skin is included in the skull, and we want to avoid that. One first idea would be to manually modify the segmentation. So instead of this purple here, we will have the pink line, but manual correction of segmentation is tedious, is prone to error, and is taking a long time, so we would like to avoid that. Still, would be nice to directly use the information of the MRI that is voxel based. So we would like to build a mesh that is with hexahedron, because then we have directly information from the MRI. Now, if we analyze one single case so if we zoom again in one of these cases, and this is depicted here. So we have 3 compartments. For example, the white one can represent the skull. Then we have in the blue one is the CSF, and then the yellow is the skin. So we know that the skull has a really low conductivity, while the CSF, for example, has an extremely high conductivity. And in this specific case, in our mesh, there's only one point that is representing the skull. So in this case, the skull conductivity is represented only in a singular point. What can happen in a standard CG FEM is that the current then will flow directly through this point without taking into account the really low conductivity of the skull. So the model itself and the method will produce a mistake, an error. If we switch if we keep the same representation of our head model, so exactly the same scenario, but we switch the method and we go for a DG FEM, in this case, the flux is obliged to to flow through edges, so not points anymore, but through edges. So in order to reach in order to pass from C1 to C2, the flux now has to flow through the skull, and in this case, the skull conductivity will be taken into account. So the error that we were committing before will be eliminated in this case, and has been proven. As a summary then, so in this case, we can directly use the voxel-based representation of the head, and this has been proven to increase the accuracy in EEG. It does not affect the MEG solution because the conductivity of the skull is not so important or evident for the MEG forward solution. But in a combined scenario, so when we want to combine EEG and MEG, then we would like to employ the same forward model, and therefore DG FEM complements, and in some cases, as this skull leakage scenario that we saw before, outperforms CG FEM in EEG or combined EMEG. So talking a bit about our tools. So the general framework, as we saw, is FieldTrip, but then FieldTrip is relying on the Symbio for a FEM EEG forward solution that has been integrated in FieldTrip. This is the general website where you can find more information about the Symbio project and the Symbio code. is totally open source, so you can download it and use it, but that would be in combination of Fortran and C or C++. So the integration of Symbio and FieldTrip makes us also, or allows for easier implementation and usage of this code. And yeah, in this paper, the integration has been explained, and every other details are explained in this paper. Also, is the one that one should cite when using the Symbio FieldTrip pipeline. The other tool that we will see today is the DueNeuro. DueNeuro is a module from Dune that is a pure C++ code, which has two interfaces, a Python interface and a MATLAB interface. And the MATLAB interface was integrated in FieldTrip by Sophie mainly. And today you will be the first one using this integration. So it's not yet publicly available. It's not. It will be in the future, but still there is some work that we have to put it on. So it's a work in progress. And today we would like to experiment with you the result of this pipeline. Some papers are already, or some works are already relying on the DueNeuro toolbox, and at this web page you can see more information about that. Yeah, so now I will go into the details of the procedure that we will be dealing with in the next hands-on session. So I identified some steps, like at first we have to create the mesh. Then we have to create our head model, where together with spatial or geometrical information, we have to add the conductivity information. Then we have to create the source model, so identify the dipoles that we want to, where we want to, or that will generate our solution. And we have to handle EEG and MEG sensors. Then we can compute the lead field, and lead field stands for the EEG or MEG forward solution. And this will be then fitted to the inverse part, which will follow, and where Simon will talk about that. And this part are the parts that are EEG or MEG dependent. So the mesh itself can be created independently of the procedure that you want to use, while the head model, from the head model on, we have to switch and do either EEG or MEG. So as to the first step, creating the mesh, there are some sub-steps. So the mesh will be created starting from the MRI. So we have to load our MRI as a T1 image. We have to realign the MRI. We have to reslice the MRI, create surface meshes. This is just for pure visualization purposes. They are lighter to visualize when we want to visualize our results and so on. We have to segment the MRI, so divide our volume into different compartments. And we have to create the volumetric mesh. So some details. It's just a reminder of every function in FieldTrip that you will also see in the hands-on session. With FT read MRI, you will load and read the anatomical data. You will have a figure like this. As you can see, the face was eliminated, and there's also a procedure that can do this anonymization or defacing within FieldTrip. Then we have to realign the MRI to, as we said before, to the CTF coordinate system with this function ft underscore volume realign. A GUI will pop up. From this GUI, we have to identify the so-called fiducials. So, for example, in this case here, the nation is selected. So you have to click and identify the nation. There's a well-evident spot for that. And then the instructions are in the ft volume realign function, but in general, you have to press N, that stands for nation, and then another figure will pop up. Or you have to select the next fiducial, and that will be the left and right periodical points. Yeah, so this is the right one, where you can see two dots that are put by the technician inside of the MRI. so that it's easy to identify them. And the left one, there's no dots, or it's less visible, but you can just play around and see where you can find the left one. Once this is done, then the MRI image has to be resliced so that the voxel of the anatomical data are homogeneous, so that the size of the voxel is the same into each direction. And this is a step that is not necessary, but will facilitate the segmentation step. And there's a function for that, FT volume reslice. In order to create surface meshes, we segment the head model, or the MRI, in 3 compartments here: skull and brain. And from that, we can create a triangulated surface mesh, FT prepare mesh. This will only be used for visualization purposes. As for the MRI, we have to identify 5 compartments. So the skull, the CSF, gray matter, and white matter. And there's with the same function, FT volume segment. And from that, we can create the mesh. So these are 5 volumetric meshes identifying each compartment. And this is the mesh that we will use for the EEG or MEG forward model solution. So after that, we can create the head model. So there will be a head model FEM EEG, head model FEM MEG, where we add the conductivity information to the spatial information. And then we have to handle the sensor. So for EEG, we should use the FT electrode realign. Could be that the electrode positions are not co-registered with our head model, so we have to make sure that they live in the same space. And we will do that. While for the MEG, the sensors are already in the native space, because indeed we are co-registering everything in the CTF space, where that is the native space of our MEG data. So then we have to create the source model. In this case, we isolated the gray matter compartment, and we created a grid of dipoles that are constrained to the gray matter compartment. And there's FT prepare source model will do that for us. In this case, the grid resolution can be varied, so we can set the resolution in millimeter. This example, I think, is a 2 millimeter resoluted grid. And we can either, in the tutorial, there would be a 5 millimeter resoluted grid because it's faster to compute. But you can also play around with these parameters, as we will see in the future. And the final step is the EEG and MEG lead field computation, and where the transfer metric approach will be used. This approach allows us to speed up the computation. So, as a summary, I might say that there are many methods that are possible to compute the EEG and MEG forward solution. Now, some methods are available within FieldTrip. That is a MATLAB-based pipeline. In some scenarios, it is important to increase the accuracy of the forward solution, and the challenge is to make it possible with a fast and simple procedure that is also compatible with different expertise and doable in group studies. And FieldTrip, SynBio, and Geneuro are trying to make this possible, so that different expertise can come together, and not only computer scientists are able to use this more sophisticated method. And that's it from my side. So if you have some questions, otherwise we can go on with the hands-on session.
Because if you want to very sophisticated model, then you use something that seems relatively inaccurate, right? I mean, you have to identify those points in the MRI, which is not that easy.
Yeah.
And then there's still quite a bit of degrees of freedom. So
Yeah.
How much difference does it make in how precise this registration is in the beginning for the end result of the entire?
Yeah, good question. Of course, you have to make sure that they are living in the same space. With the EMEG is relatively easier because, yeah, for EEG, I don't have like a quantitative reply.
Just half a centimeter up here. Just a few points. You
Yeah.
back of the head have a centimeter.
Yeah, exactly. Like in this procedure dataset here, it's quite accurate because the procedure was there was an ear mold, and they basically in the MRI they're the same when they're measuring the EEG. So here it's quite easy. Normal procedure, as you described, of course. If you want to find the preocular points on an MRI, 1 millimeter here is already 2 millimeters here. So basically, if you have a little bit offset here, it propagates through the whole head. Like my experience with co-registration is especially the front part is not so problematic because finding a point at the nose here, it's easy. In the MRI, it's also quite clear. But at the ears, of course, I think they can easily be messy. And
But you should also do the MRI scan that are marked with a vitamin B.
yeah, that's what you saw on the picture. Can you go back to the slides? I think. Yeah, they were not random points. They were like these.
Yeah, these
Can
2
s-
points here.
Yeah, these are
These are
like vitamin E or this is kind of galenium. Something visible in the MRI. Yeah.
yeah, and for the nation as well. So this point is not part of our.
But putting the question from another perspective, do you have a way to validate whether this alignment is satisfactory for your model? So once you do this step, you do this step for the first time.
Yes.
Do you understand that this match within the two spaces?
Well, for example, here there's a visual. There's a visualization. So in the yellow part is the. This is working, yeah. Also, the yellow part is part of one step of your head model. So, for example, this is the surface of the scalp, and plotted are the electrode position. So you can visually see that so far the co-registration is not so bad. Plus, there are systems that you can use to this polymus system. Yeah, this is to acquire the position. And yeah, this is not about co-registration. It's about the correct acquisition of the electrode position. Yeah. Yeah. Maybe she was first.
You just use like the general electrode configuration for say EEG channel EEG layout. Can you feed something like that into this with your individual subject MRI? Even though it's not.
Yeah. Also, like the templates are available.
Even though the cap may not have been exactly in that space for that individual subject.
Yeah, I think it's basically you go for the template approach. Like you just take a template. Yeah, it's of course feasible. Of course, then you have problems with variation. Like a template is just a template for one subject. If you have imagine like my head and Carla's head, of course, the template doesn't apply. So then you of course are prone to errors already. So it's always better to record electrodes, but if you can't, there might be good reasons for that. But then you can still use templates for that.
With respect to the MRI head model, that's the one thing, the data that you had, that was using like a temporary sequence. But from what I gather, like scale is quite important.
Yeah.
So what about like using amplitude range sequences, for example?
Yeah.
They have much better basically, well, you can see the skull, right?
Yeah.
See, just different tissues that you see.
Yeah,
It's like almost identical at first glance to an amplitude range. But in particular things like skull, it just shows different structures.
Yeah, exactly. So in the ideal world, we will have CT of patients, or because then it's very easy to identify the skull compartment, the bones. Yeah, exactly. But so in the ideal world, we will have CT. Otherwise, this model was created with T1 and T2 images. So as you said, so that for example, when the spongy part and the compact part of the bone were separated. Where is it? Yeah, here. So by using the T2 image, was possible to identify and separate between the spongy and compact part of the bone. Yeah.
Right. Yes. Yeah. You showed more depending on the
Yeah.
How important is the resolution of your small places? Is that can be pretty tiny? Fairly visible.
Yeah.
Right?
Yeah. So plays a role. Yeah.
Is there any sort of like, I don't know, common experience was scanning at 1.75 millimeters or 1 millimeter?
Below 2 should be still okay, but of course if you have one, yeah, will be better.
Essentially, to certain really when kind of planning an experiment, right? Scanning at 1 millimeter, take subject, take 5 minutes, 6 minutes, it'll probably cost you $100 per subject. If you're aiming for higher resolution, to T2 and something like that, that usually goes to probably like 250 or 300. Not really much more work or anything like that. You just need 10 minutes of the MRI, like 25 minutes of the MRI.
Yeah.
Doesn't really hurt anybody except for the work.
Yeah.
The question is, do you want to make a set of a wallet or
I think in our institute we always use a 1 square millimeter resolution. Yes. I don't know. This one. Yeah. Yeah. So this is our default.
Yes.
Yes, we do that.
Yes. Yes.
Yes, usually that's our standard procedure to do exactly this, to use the T2 for the skull segmentation. Yes. And then we also usually have DTI data for anisotropy in the white matter. Additionally, yes. Yeah. No.
Yeah. No, within FieldTrip, yes. Yeah. Yeah. Yeah, so yeah. Okay, thanks. For the first question, yeah, T1 and T2 can be analyzed in FieldTrip, and you can play with some masks to isolate the skull from a T2, and also some erosion procedure to isolate, in this case, the spongy part. So everything was done within FieldTrip. And as to the second question, is a good question. There's there's a big debate on that. So there are some parameters which are considered to be fixed, but we don't have in vivo measurements. There were some measurements of conductivity in dead bodies, but it was proven also that the conductivity values are dropping immediately after that, so it's not really reliable on that. EIT is also not a good instrument to detect the conductivity of tissues. So, for example, when I mentioned this skull conductivity calibration, is a procedure that I'm referring to one that is used in our institute, where we are combining the EEG and MEG data, because we can, maybe Sophie can explain even better, because she's working on that.
So what we usually do is we try to be very accurate in source reconstruction in epilepsy patients. So we really go for accuracy. So we try to calibrate the sky connectivity of individuals. And we start from combined EEG, MEG measurements of the somatosensory evoked potentials that you saw. And then we kind of use the MEG for the source location, the EEG for the orientation, and then the MEG for the magnitude again to reconstruct the dipole. And then in the end, compute the residual variance to the data and pick the connectivity in the end that yields the best residual variance. So we have a very sophisticated pipeline, which of course isn't usable for the standard experiment, which requires a lot of data. So of course it's better to have some sort of optimization at this point, and especially the EEG is very depending on connectivity values. But I guess, also you can, if you don't have a choice, you have to rely on the literature values. And it's true that also they varied over time. So I think it used to be a higher connectivity for the sky in early days. Yeah, that's true. So there's still a lot of research to be done in this area. It's a kind of long procedure to calibrate it, but we basically do a reconstruction of the PN20 component of the somatosensory data and kind of optimize it using the different strengths of EEG and MEG. And then we compute the residual variance to the EEG data of the optimal dipole, and we repeat that for a lot of connectivities of the skull. And then we compare the results, and then we check for which connectivity we get the best fit. Yeah, it does. Yeah. Yes. Yeah.
And for the white matter, we can use DTI data. So relate the tensor, the diffusion tensor to the conductivity tensor. So somehow is individualized, I would say. But anisotropy, we wouldn't use anisotropy for the whole head, for sure, because then the computational cost will also explode. The anisotropy part, no, not so far. Yeah.
Possible to perform a multimodal segmentation, for example, you have the CT and the T1 when it's a fusion image, then you base your segmentation on all three, or you have to essentially pick one?
You can combine results and you can apply the same pipeline to each image, I would say. And then you can use MATLAB functions to kind of combine the results that you get. But there's, as far as I know, there's not one unique function that where you can fit in all the image and will do all the job for you, as far as I know. Yeah. Cannot hear the question. Maybe I can give you the microphone.
But I don't know if it's running over the side.
Yeah, it's running.
I'm sorry, the question was about previous neurosurgery.
Yeah. Yeah. So, for example, for epilepsy data, some of the patients have to be implanted with internal or deep electrodes, and so you will have skulls, holes in the skull. And this also can be represented. So you can, in this case, you will have a CT for sure. So you can segment the CT. You can include the skulls and the holes of the skull, and then you can modify, and you will see a huge difference in the forward solution and in the source reconstruction, because you're altering, or if you're using the wrong model in that sense without taking into account, for example, the holes, then the topography will be completely different. And yeah, for brain lesions, is this replying to your question, or you meant something else? Okay. Yeah. Yes. So, for example, in this case, the gray and white matter, or the whole brain, was segmented in FieldTrip, in FreeSurfer, and then the result was included in FieldTrip. There's also a tutorial online which is guiding you. So, FreeSurfer is not directly integrated in FieldTrip, but you can run it separately, and there's also a tutorial how to manage the different coordinate system and how to bring FreeSurfer and FieldTrip together. Okay, maybe if there are no further questions, we can go on. So there's a lunch break between 12 and 13, hopefully, because there was no coffee break before. Maybe we can ask the organizers. And yeah.
So the coffee, our break,
Okay.
was not the official coffee break. That was in the morning. So
Ah.
our breaks are just breaks. So we can buy our own stuff.
Okay.
Lunch break means we all get our own stuff.
Okay. Okay. I see. Okay. Thanks. Yeah. Yeah, it was at 8. Yeah. Yeah. Okay. Yeah. Okay. Then in general, maybe we can also. There are not so many Ubuntu machines here. So if you want, we can have like for the people who are interested in the MEG forward model reconstruction, we can have a demo, a live demo. So we can work from our laptop here and show the various steps and make it run in the big screen if you want.
And we can ask Carla.
Yeah, or you can maybe think about that during this lunch break, and when we are back, we can maybe settle a subgroup of people and do the demo, live demo only for the people who are interested in the MEG part. Yeah. Okay.
Okay.
Then see you later.